So in a previous example, we looked at the integral of x e to the x, differential x, and we used integration by parts to find that the antiderivative of that was x e to the x minus e to the x plus the obligatory constant. So we're going to repeat this problem, but we're now going to look at the definite integral problem, where we're going to look at the integral from 0 to 1 of x e to the x differential x. And there's really no difference here, but I just want to show you how to deal with these limits of integration while you're working with integration by parts. So the trick here will be, just as before, we're going to let u equal the expression x. A consequence of that is that du is equal to 1 dx. And we're going to let dv equal e to the x differential x. By integrating, we get that v is equal to just e to the x. So this is exactly the work that we did in the last example, but I'm just showing you that again. So by the integration by parts formula, we'll take the product of u and v, so that's x e to the x. And what's new now is we're going to say that we're going to evaluate this from x equals 0 to x equals 1. And then again, so that was the u times v minus the integral of v du, which is e to the x dx in this case. And again, what's different here is we're going to include the limits of integration. Okay. There's lots of ways you could then continue to handle these limits of integration. I find it easiest to just not evaluate them unless they're going to evaluate to 0, and just continue with the integration process. The antiderivative of e to the x is e to the x. This is also evaluated from 0 to 1. And then if you like, you could think of putting that into just a single expression that looks like this, evaluated from 0 to 1. We're ready to evaluate it. We get 1 e to the first minus e to the first minus parentheses 0 e to the 0 minus e to the 0. If we clean this up, we get e minus parentheses 0 minus 1, where this cleans up to 1. So there's an example of using integration by parts with limits of integration.